Hello friends, in this very special video I'd like to solve the following problem from the Lowell Putnam Mathematical Competition 2016, problem B6. We wish to evaluate the following series from k equals 1 to infinity of minus 1 to the power k minus 1 over k times the series from n equals 0 up to infinity of 1 over k times 2 to the power of n plus 1. This problem is very hard. I'd argue it's legendary because it's from Putnam Competition, and if you know anything about it, problem B6 is the very last question on Putnam test, and it's usually the hardest. You shall see in a moment. But my hints, if you would like to try it yourself. First of all, notice that 1 over a plus 1 can be expressed as an integral from 0 to 1 of x to the power of a dx. Second, you should check first that our double series converges absolutely. It's pretty easy to check that, because the main method of solving this problem, it is crucial to exchange the order of summation multiple times. So Fubini's and Tonelli's theoremata will be very useful. So if you don't know these theorems, maybe look them up on Wikipedia or something. And moreover, the following three lemmata will be useful. The first lemma is that 1 plus x times 1 plus x squared times 1 plus x to the fourth power and so on. This infinite product can be expressed as the infinite sum 1 plus x squared plus x cubed and so on for every x greater than minus 1 and less than 1. Moreover, second lemma, the limit as t goes to 0 of t natural log of t is 0. It's pretty easy to check that. And the third lemma is that the integral from 0 to 1 of natural log of 1 over 1 minus x dx is 1. So pause the video if you'd like to try it yourself, and I will see you in a moment. Okay, so first thing which I want to do is to prove the stated lemmata. So let's prove the first lemma. So the proof is quite straightforward. So first of all, let's consider finite product 1 plus x times 1 plus x squared, 1 plus x to the fourth power, and so on, up to 1 plus x to the power 2 to the n. And now it's pretty easy to see by multiplication that we can get every possible combination of product of ones or powers of x with even exponents, with exponents which are powers of 2. And on the other hand, every non-negative integer can be written as a sum of distinct powers of 2 in exactly one way, the binary system. So this product, for example, if we multiply once, we will get 1. If we take x from this parenthesis and ones from the other parentheses, we will get x. If you take 1 from the first parenthesis, x squared from the second, and ones from the other parentheses, we will get x squared. Then we will get, if we take x from the first parenthesis and x squared from the second, and ones from other parentheses, we will get x cubed. And so on, every power of x will appear. The highest will be x to the power 1 plus 2 plus 4 and so on plus 2 to the n. It's 2 to the n plus 1 minus 1, in fact. And now, taking limit on both sides, taking limit on both sides as n goes to infinity allows us to deduce that 1 plus x, 1 plus x squared, 1 plus x to the fourth power, and so on, infinite product equals this infinite sum. For x from -1 to 1, because we know that our geometric series converges from -1 to 1. Okay, so that concludes the proof of our first lemma. Our second lemma is also not that difficult, because this limit as t goes to 0 of t natural log of t, we will compute this limit using the L'Hopital's rule. So let's first write it as the limit as t goes to 0 of ln t over 1 of t. And now we have a classic situation that our denominator goes to infinity, so we can use the L'Hopital's rule. Maybe write it. The L'Hopital's rule. By the L'Hopital's rule, we get derivative of natural log of t is 1 over t, and derivative of the denominator is -1 over t squared. So it's limit as t goes to 0 of just minus t, which is 0. So that concludes the proof of our second lemma. And finally, the third lemma, we wish to compute the integral from 0 to 1 of natural log of 1 over 1 minus x dx. Okay. And now, how can we do it? Well, first of all, we can put minus in front of our integral, and we will get natural log of 1 minus x dx, because of well-known property of logarithms. And now we can proceed using integration by parts, namely our u function will be natural log of 1 minus x. It will be differentiated, so u, derivative of u is it's 1 over 1 minus x, and also derivative of inner function will be minus. And the second function will be, let's say, will be x minus 1, because the derivative of x minus 1 is 1. And exactly, our function is just 1 times this natural logarithm. So now, integrating by parts, we get that our integral is minus integral from 0 to 1. No, sorry. Minus in front. We multiply these terms. And we evaluate it from 0 to 1, because our integral was from 0 to 1. And now we have minus still in front, and we subtract the integral of these numbers. So we subtract, so plus integral from 0 to 1 of minus 1 over 1 minus x times x minus 1 dx. And now let's see. If I put 1, yes, exactly. It's that moment where I will use the second lemma, which I have proven recently. We will get limit as x goes to 1 of x minus 1 natural log of 1 minus x. If I put 0, there is no problem. Natural log of 1 is 0, so this disappears. And we have integral from 0 to 1. And here we have just minus 1 dx. No, here we have integral of 1 dx, because here we have different signs, so it's integral of dx. And now by lemma number 2, this first limit, it's just limit as, because this goes to 0, this goes to 0 as well, so by our lemma, we know that this entire number is just 0. So we get just x evaluated from 0 to 1, it's just 1. And that closes the proof of our third lemma. Now the fun part. So we have just proven our 3 lemmata, and now it's time to proceed with finding our series. So recall that we wish to evaluate the series, the sum as k goes from 1 to infinity, minus 1 k to the power minus 1 to the power k minus 1 over k. The second sum is over n, k2 to the power of n plus 1. First of all, I will first show that this double series converges absolutely. So first things first, this sum converges absolutely. How do I know that? Well, if I take my double series and I put absolute value on my terms, we see the following. So we just get, so let's find upper bound on our series. So first of all, let me put it lower. So right, okay, here we have 1 over k, and this term 1 over k times 2 to the power of n plus 1, well, if I diminish the denominator, I will get bigger fraction. So I can omit this number 1 and inequality holds. And now I can write that it is series of 1 over k squared times the other series from 0, 1 over 2 to the power of n. And it's well known that this first sum converges. In fact, if you are fancy, you can say that it equals pi squared over 6, but we just need to know that it converges. It's well known that it converges. And the second series is just 2, because it's sum of reciprocals of power of 2. So this definitely is less than infinity. So our sum converges absolutely. Why do I need that? Because now, knowing that our sum converges absolutely, I can use Fubini's theorem. We can use, let's write that in green, we can use Fubini's theorem, which allows us basically to exchange the order of summation. So originally we had sum from k equals 1, and then n from 0 to infinity, 1 to the power k minus 1 over k, 1 k to the power 2n plus 1. And now by Fubini's theorem we can change the order. So we can first sum over n, and then we can sum over k. Okay, very well. And now what I will do is, because we know that our series still converges absolutely, we can group our terms. So I will group the terms of my second series in pairs. So term for k equals 1 with term with k equals 2. Then I will group term with k equals 3 with k equals 4, and so on. And I will get, first I will have terms with odd indices. And then I will have terms with even indices. Okay, very well. And now, what can we do now? So now let's simplify it a little bit. So it's series from n equals 0 to infinity. Then we have series from k equals 1 to infinity. 1 over 2k minus 1, 1 over 2k minus 1, 2 to the power of n plus 1, minus 1 over 2k, 1 over 2k, 2 to the power of n plus 1, close parentheses. Now, the tricky part. The first two sums will stay the same. The first two sums will stay the same. And now, by first or second hint, I don't remember, this fraction right here, it's just integral from 0 to 1 of x to the power 2k minus 1 to the power 2n dx. Okay, and likewise, this part over here, it's integral from 0 to 1 x to the power 2k 2 to the power of n dx. Wow, what's happening? So basically we have introduced two integrals, and it looks like we are complicating our problem, but in fact we are not. You shall see in a moment. So now let's combine these two definite integrals from 0 to 1. Let's combine them into one integral. So it's x to the power 2k minus 1 to the power 2n over 2k minus 1 minus x to the power 2k 2 to the power of n 2k dx. Okay. And now another funny part. Let's notice it's pretty easy to see that this part is non-negative. Why is that? Well, first of all, we have numbers from 0 to 1. For numbers from 0 to 1, the higher the exponent is, the smaller entire number is. So here we have smaller exponent than here. So this numerator is greater than this numerator. And in the denominators, here we have lower denominator than here. So entire fraction must be even bigger. First fraction is bigger than the second. So this is non-negative, which allows us to use Tonelli's theorem by Tonelli's theorem. Tonelli's theorem allows us to exchange again the order of summation or integration. It's very similar to Fubini's theorem, but in Fubini's theorem we need to check the absolute convergence. It's the assumption, and in Tonelli's theorem we need to check that our function is non-negative. Then we can freely exchange the order. So I will do that. So I will put this integral first, and then I will put one sum, and I will put another sum. And here we have x to the power 2k minus 1, 2 to the power of n, 2k minus 1, x to the power 2k, 2 to the power of n, 2k dx. Okay, and now what I will do is to combine. First series remains the same, and the second series I will write it in the following manner. Okay. So here we have odd powers, odd indices appear with a plus, even appear with a minus. So we can write that as minus 1 to the power k minus 1, x to the power k 2 to the power of n over k. We can do that because it's well known that this series converges absolutely for every number between 0 and 1. And we are considering only variables between 0 and 1. So this sum is exactly the same as the upper sum. And now I will write it in the following manner. I will write it as minus 1 to the power k minus 1, x to the power 2n to the power of k over k, okay, dx, because still we have integral in front. And now I will use another well-known fact from mathematical analysis, namely that the function natural log of 1 plus t, it's t minus t squared over 2 plus t to the third power over 3, and so on and so on and so on. It's a well-known fact, and it's true for t, let's see, from minus 1 to 1. So, and here, this very sum, it's like that. So, we will get, by this fact, integral from 0 to 1 of the sum from n equals 0 to infinity. And here we will have natural log of 1 plus x to the power 2 to the power of n dx. Okay, it's something. One infinite sum disappeared. And now, what can we do? Well, here we have a sum of natural logarithm. By well-known property, sum of logs is log of a product. So we have natural log of product of 1 plus x to the power 2 to the power of n dx. Okay, and now by lemma number 1, we know that this infinite product, which is 1 plus x, 1 plus x squared, 1 plus x to the fourth, and so on, we can replace this infinite product by the 1 plus x plus x squared plus x cubed and so on dx. Okay, and now I need another page. Minute. And now we have integral from 0 to 1, and here we have infinite geometric progression. By well-known fact, it's 1 over x dx. And now, finally, by lemma number 3, we know that this integral equals 1. And here we have our result, our double infinite sum, as k goes from 1 to infinity of 1 minus 1 to the power k minus 1 over k of a series of n equals 0 to infinity of 1 over k to the power k times 2 to the power of n plus 1. This double infinite product, it's just 1. It's amazing. It's a truly beautiful problem. Remarkable solution, in my opinion, because we have used many well-known facts from analysis. Taylor series for natural log, Fubini's theorem, Tonelli's theorem. We have changed fraction into integral. We have evaluated integral along the way. We have checked absolute convergence. We have made product, infinite product. We have changed it to infinite sum. Many other things. So I hope that you learned something, that it was entertaining for you. For my students, if any of my students is watching me, don't be afraid. It's even on mathematical studies, these types of problems are not covered because they are too difficult. They are perfect for ambitious mathematical Olympiads and competitions, like Putnam Competition, which is remarkable, excellent competition for the very best mathematical students. Okay, and one last thing. I wish I'd like to call my fellow YouTubers, mathematical YouTubers, because many of you know who I'm talking about. Many of you freely exchange order of summation integration without properly justifying that it can be done. My message is for you. If you are doing pure math, be rigorous. Use Tonelli's theorem, use Fubini's theorem, and justify them, as I have done in my video. Don't be sloppy, it's my message. By the way, I don't want to be mean, I just want to be rigorous. Okay, so long. So thank you for watching. I hope that you enjoyed it, and I wish you a nice day. Goodbye.